Okay, so continuing on the topic of DMA, there is one other issue that we need to be careful of while working with DMA, which is related to the cache hierarchy, right? And this is something which again I have mentioned briefly, but just sort of recapping it over here. Typical SOCs nowadays have multiple CPU cores. I might have, for example, core 0 and core 1. Now, the L1 caches, level 1 cache, is typically small but is also local to the individual processor. So, the L1 instruction cache and data cache corresponding to core 0 are separate from the instruction cache and data cache for core 1. The point is L1 cache is extremely fast, usually 1 cycle access, right, or very close to that. L2 cache is typically shared among cores, meaning that I could probably have core 1 and core 2 having the same L2 cache, right, and that could be much larger. It could be on the order of a megabyte or so. Sometimes I will have L3 cache which is shared among possibly even different clusters of cores or even 2 different chips sometimes in some cases, right. So, whether the caches are shared, whether they are individual to each processor is all design decisions at the architecture level, the CPU architecture level. But the point is, what they do is that they enable us to access this main memory, which is our DDR RAM, which could be in the gigabytes range, much more efficiently. The problem of course is DDR has high latency. If I try accessing a particular location in DDR, then it can take potentially even thousands of clock cycles to get to that particular memory location, after which I should be able to read a burst of data fairly fast, okay. But if I want to do random access and I want to sort of read from multiple different locations, then it can become problematic. So instead what we do is we observe that typically when people are accessing something in memory, they tend to reuse that quite a lot, okay. So anytime the data is read from memory, it is first stored in L2 cache, then a copy of it is put into L1 cache, and the CPU basically talks only to L1 cache. It never talks directly to L2 or to main memory, okay. So that's good. It means that everything is very fast while the CPU is actually working. The problem is, if I have a DMA device which is also trying to directly write or read, right, so from somewhere in memory, right. Let's say that, for example, as we see in scenario 1 over here, core 0 writes something into its L1 cache, okay. By default it just keeps it over there. It's not going to keep going and telling main memory, okay, I wrote something over here. The reason is because if I kept doing that, then I would be running slow again. So core 0 thinks that it has full access to the that particular memory location and just handles it in L1 cache. It has modified it, right, because it's performing some computation. During that time, the DMA device tries to read from that location. It ends up reading stale memory because whatever was in the cache over here has not got written out. The second possibility is the core 0 has already got some data sitting in cache. DMA now goes and writes some new data into the main memory. The problem is the core doesn't know that, right. Otherwise, once again same story, the only way it can know that is by going on checking from main memory whether something happened, in which case we are back to having a slow system, right. So both of these are problems related to this concept of coherency, right. And typically how cache coherency is implemented is using various kinds of cache coherency protocols, okay. And what is usually done is the cache coherency protocol is used in order to ensure that the caches of multiple cores are kept coherent, because I could have the same problem between core 0 and core 1, right. Let's say that core 0 has read something from main memory and is modifying it. When core 1 tries to access it, I need to make sure that I don't have a problem and that I'm actually going to get correct data. Now this is relatively easy because they are both sort of sharing the same access path to main memory, right, because if core 1 tries to access a certain location, and if it was, what I can probably do is the moment core 0 loads something over here, I basically mark it as now this is locked by core 1 somewhere in the L2 cache, which means that when core 1 tries to access it, it will go here, find that okay, wait, there is a problem, I've got this changed over here. The simple way might be that I just sort of have some small circuit that basically snoops on the bus and says anything that's going into these locations I also need to update them out here. There are multiple ways of handling cache coherency, The point is that when you are running between cores, it can be handled in a certain way. But when DMA is doing this, it's bypassing all the caches completely, which means that it doesn't have any notion of these caches, it doesn't care about coherency, it directly goes and tries to manipulate main memory, right. So the solutions for this, of course, is something, one of them is what's called coherent DMA. What happens in coherent DMA is that you need modifications at the hardware level that are continuously checking on whether these addresses that we are interested in are being modified in the caches. So it actually requires some kind of support from the hardware in order to do that, right. And as you can imagine, that also does make it a bit slower because there is some extra checking that's happening, right. So even though I am trying to access something from cache over here, it means that I need to be careful and make sure that whatever the DMA is doing and what is happening in the cache are not ending up causing these problem scenarios, right. The other approach, as we saw, was what we can use for streaming DMA, where I basically say, look, I just have a chunk of memory out here, I am going to sort of reserve that, don't use the cache at all for that chunk of memory, and explicitly make sure that you do synchronization. In other words, if at all anything is done, the DMA writes into a certain chunk of memory. If the CPU needs to read it, it first has to run that sync command, make sure that everything the DMA has been completed, and then read it into its memory, and so on, right. So the CPU has to explicitly ensure that there is no DMA going on before accessing any chunk of memory. So this part of it, right, the streaming DMA is explicit synchronization, it's manual cache management, because effectively what we are doing is that we are saying that the CPU has to ensure that the DMA has completed before it tries to access any particular location in memory. It results in a more complex driver, but it can give much better performance. Coherent DMA is something where we say, okay, I don't want to think about this problem, somebody solve it for me. The hardware snoops on the caches, it sort of keeps track of which addresses are being accessed and tries to do some kind of automatic synchronization. It simplifies the driver code, meaning that from the user's point of view it looks simpler, but it can actually have an impact on performance, right. It is also possible to say, just don't cache this location and this set of addresses at all completely and still try to access them directly. Now that's obviously going to be the poorest performance because it bypasses the caches altogether, right. In practice, what we find is, especially when we are talking about high rate FPGA peripherals, the DMA with the MM2S and S2MM is the way to go, right. The streaming DMA approaches are the ones that are going to give you the maximum throughput. So to summarize everything that we have talked about memory so far, virtual memory provides isolation. How is it implemented? Via the memory management unit. What does the memory management do? Translation, right, address translation. So all of these, there are a number of different terms out here that you need to unpack and make sure that you understand the terms and where they apply, right. The address spaces are separated primarily for security and also for stability of the system in some cases, but security is probably the main reason. You do not want one program maliciously or accidentally sort of getting data out of another one. Now coming to the context of DMA, right, there are a number of things that you need to keep in mind. One of them is contiguous buffers. How do we achieve that? Reserving memory, right, and typically have a separate driver whose job is basically to manage these kind of contiguous allocations, right. So both of these are at the operating system level changes that are made to ensure that DMA can progress smoothly. The IOMMU adds one security layer because otherwise DMA has the possibility of directly trying to access physical addresses, which can cause other problems of its own. And as we just saw, right, cache coherency is also critical. How do you handle that while still getting good performance? Probably the best preferred approach would be to use the streaming DMA solutions.